We have so far established the existence of the Mott insulating phase and incompressible insulating phase in the extreme limit of T over U equals 0. And now I want to do a perturbation calculation when T over U is finite but very small. Let us first write down what this Mott phase, a Mott state looks like. So M for Mott and N for N particles per site. And first pictorially, this looks like this. I have L sites. On each site, I have N particles. In terms of operators, we have the vacuum, and on the vacuum, I will act with a creation operator. I need to create N particles on site I, so this will be acting N times. It will be divided by N plus 1 factorial square root to normalize. And note, I didn't put an I here because we have the same number of particles on every side, so I will just put an N. But where do I create these N particles? Well, we have to create them on every side, so we have to have a product of such operators from site 1 to site L. So this is the Mott insulating phase. And as I said, it looks like this. Pictorially, if we draw a picture of it, it looks like, well, we have the chain, we have our sites, and on every site we have N particles. I'm just going to draw one circle to represent a particle. So we have these particles like this, they cannot jump around. Now I want to perturb this state. What do? I can add a particle or remove a particle. Let's say I add a particle. If I add this particle here, on some site here, this particle will feel the same potential energy here as it will feel here, as here, as here. So there is no reason for it to be confined. These blue particles, if you want, they are confined, they cannot move, because if one of them jumps on the other particle, there will be a big energy cost, it has to jump back. But now that I have a layer of these particles, if I add another particle, this particle is free to move all the way around. So this is the doped Mott state. I have my Mott state, I dope it by adding a particle. For that reason, I will call it P, particle doping at N particles per site, which means I start with N particles per site, and I dope by adding one particle. This is going to be the Mott state. I take the Mott state, which has N particles per site. I create one more particle on some site I. Of course, we have to divide by the square root of N plus 1. But where do we create this particle? This particle can be created anywhere. And therefore, we have to do a sum. In fact, it is a superposition of I from 1 to L, so that we can allow the particles to be created anywhere. And of course, we need to normalize, since we are adding L such terms, because we want Pn to be equal to 1. I have to normalize by dividing by the square root of L. So this is the particle doped case. I add a particle to the Mott insulator. Now we can also dope by removing a particle. If I remove a particle here, that leaves some room for the particles in the Mott phase to move around. That will also give me the possibility of transport. So let us dope now the system, this Mott phase. We will dope it by creating a hole, the H for hole here, on a state with N particles. This is equal, as before, we take the Mott phase, we now destroy a particle on site I, normalize by dividing by the square root of N. This can be done anywhere on the lattice, so I have to sum from 1 to L and normalize by dividing by the square root of L. And of course, as in this case, we have Hn equal to 1. So now I have the Mott phase, we have the particle doped state, and we have the hole doped state. Now we want to calculate their energies. So the energy for the Mott, that's equal to Mott state, the Hamiltonian Mott state. The energy for the particle doping is the same, it's just the particle doped state, Hamiltonian particle doped state, and the energy for the hole doped state is Hn. Okay, so how do we calculate these quantities? I will show the calculation for this case. The other cases will follow in exactly the same way. I will show the calculation for this case and simply give the results for these other cases. So, to calculate the energies I just mentioned, we need to keep in mind first that the states are normalized like this, and that they are orthogonal to each other. So if I take the inner product of a state with another state which is different in any way, we must get 0. Okay, we need this in the calculation we're going to do. So now to calculate the energy of the particle doped state, as I said, this is equal to the particle doped state, Hamiltonian particle doped state. But I must insist that this is the energy of the state only in perturbation calculation, first order perturbation, because this state that I'm showing here is not an eigenstate of H. So this cannot be the exact energy. This is the energy to leading order in perturbation. So let us write this out. We have the particle doped state. What is that? That's 1. That's the sum over I of n plus 1 n. This is at site I, summing over I from 1 to L. Sandwiching the Hamiltonian, and on the other side we have also 1 over the square root of L, the sum of n plus 1 n. Now we have to be careful with our indices. I don't want to use the same index here as I used here. This is I from 1 to L. I'm going to use an index j from 1 to L here. So this is site number j. So let's write the Hamiltonian in. So that will be now 1 over root L, 1 over root L. We'll put it here, 1 over L. Then I have the sum over I and j, both going from 1 to L. I'm going to have the bra on site I. I will keep writing this so that you don't get confused. And then we have the Hamiltonian, which is minus T, the sum over I. Let me say, I cannot use the same index here, so let's say the sum over L from 1 to L of A dagger L plus 1 AL plus AL dagger AL plus 1. This is the kinetic energy term, the hopping term, plus U over 2, the sum over L, again from 1 to L, of NL plus 1. And then we have the ket N plus 1, and this is site J. So now we need to calculate these two terms, right? We have this term sandwiched between these two states, and we have this term sandwiched between these two states. So I'm going to write them separately. 1 over L, the sum over I J, L, all going from 1 to capital L. Then I have minus T. And then we have this, N plus 1. And again, I will write that this is site I. And then we have here A dagger L plus 1, AL plus AL plus 1 dagger here. And then the ket, N plus 1, and this is site J. So this is the first term. Now, the second term, I'm going to write it on the line here. I'm going to write plus U over 2. Again, we have the same thing here. We have the square root of L from, we have 1 over L here, and we have sum over L here. So we're going to have 1 over L sum over I, J, and L. N plus 1, N. And then L minus 1, N plus 1. This is site J, and this is NL minus 1, so this must, not this, but this must be minus 1. So we need to calculate these two terms. First, notice that here, if this destruction operator acts on some random site, let's say it acts on site number 2, it will remove a particle from here. This will create a particle on site number 1. So this will be n minus 1, this will be n plus 1, which is very different from this state, and so the inner product will be 0. So there are many terms which will give us 0, and we will only get non-zero if L plus 1 matches J and L matches J minus 1, therefore. Okay? Because this gives us the hopping from L plus 1 to L. So if L plus 1 matches J, the AL dagger must match the site before it. So J and L are stuck together. L plus 1 is equal to J. Okay? So that means I don't have a sum over J and a sum over L separately. We have only a sum over one of them, either L or J. Okay, so this, let me write it like this. This must match site J. These two must match. And when this acts on this state, that's going to give us a square root of n plus 1. And when this acts on the neighboring site, which has n particles to create another one on top of them, it's going to give us another square root of n plus 1. Okay, so we have now an n plus 1 coming from these two terms acting on this. And this state here now must match exactly this state, otherwise we get 0. So how can that happen? Well, that can happen if L matches I. Okay? So what will we have here? We will have 1 over L, that's this term. We have times minus T, that's from here. And then we have n plus 1 from there. And now we have the sum over the remaining index here, whichever one we decided to keep in the end. We have to sum over it. That gives us an L. Right? So we have an L here. But I only talked about this term here. What about this term? Well, this will do the same that this term did, except in the other direction. If this one takes a particle from L plus 1 to L, this will take a particle from L to L plus 1, but all the terms will be the same. And so what do? Well, we just multiply by 2. Okay? So now this is the answer to this operation here. Now, what about this one? Well, this one is in fact easier because this operator, these operators here, NL, these do not change the occupation number. These do not change the number of particles on the site. This operator is diagonal. So L must match J and I must match L. So here we have now the following. We have the U over 2. We have the 1 over L. We have N times N minus 1 on the sites where I have N. Okay, because we're summing L over all sites. Some sites will have N. Most of the sites will have N. One site will have N plus 1. So this is going to be, there are L minus 1 sites that have N particles per site. So this would be N minus 1. And there is one site which has N plus 1. So that would be plus that one site which has N plus 1 times N plus 1 minus 1. So that's just an N. Okay? And this happens, we have to sum over one of these indices because J must match L and I must match L, but we are summing over L, so there will be an L term left here. Okay? So now we need to put these two terms together and simplify, and that will give us EP of N. So we found this expression now for the average of the Hamiltonian in the particle doped state. Again, I remind you, this is perturbation calculation first order, and this calculation was done in the one-dimensional system. We only have from I to I plus 1 or J to J plus 1 and so on. If we had D dimensions, each dimension will contribute hopping, because the particles can hop either along the X, for example, or along the Y, and so on. So that will simply add a multiplicative term here, D, for the D dimensions. Nothing else will change. So let us keep the D here and take the general result for all, for any dimensionality. And so then the simplified version of this equation will simply be L U N plus 1 and minus 1 divided by 2 plus U times N minus 2 T D N plus 1. Okay, system here. So this is E of the particle doped state. In the same way, we can calculate E for the Mott state, E, M, N. Now that, in the Mott state, there's no hopping. So in the Mott state, we will only get the L, U over 2, N, N minus 1, and other contributions are not present. And for the whole doped state, we will get the same term here. And then we will have other terms because there's a hole in there and because the particles are hopping. And so we'll have minus U N minus 1 minus 2 T D N. So these are the three energies that we were after to first order in perturbation calculation. Now, as I mentioned before, when we have the energies, the ground state energies of certain states, we can calculate the potential, we can calculate the chemical potential. So if I want the chemical potential to add a particle to the Mott phase, it is just E of Pn minus E of Mn. So let us write these down. Let us take mu I'm going to put here add. Okay, this is the chemical potential to add a particle to the MOT. That's equal to E of Pn minus E of Mn. Now, if you remember before, when I drew the phase diagram, the vertical axis was the chemical potential normalized by the coupling. So let me divide by U. Divide this by U. And then simply subtract this from this. Okay, so that gives us N minus 2dt over U times N plus 1. So you see already this is the perturbation parameter we have, T over U, which is supposed to be small. In the same way, we calculate the chemical potential to remove a particle. So mu remove, that's just equal to EMN minus EHN. And again, we will divide by U. And just by doing the subtraction, we will find that this is equal to N minus 1 plus 2d N T over U. Okay, so we have the energies and we have the chemical potentials to add or to subtract to remove a particle. What do we do with that? Well, now let's try to draw the phase diagram. As we said before, this is mu over U. This here is T over U. We showed before that this is 1, 2, 3, 4, etc. We showed before that when T over U is 0, when we're here, this has 1 particle per side, and this has 2 particles per side, 3 particles per side, and so on. So now let's apply these equations here that we got. When n is 1, let's take first the lower chemical potential, the chemical potential to remove. When n is 1, n minus 1 is 0, so I just have this term. And it starts at 0, of course, so it goes something like this. Straight line. We take we consider the chemical potential to add a particle. N is 1, so we start at 1, and then we have a straight line with a negative slope. So it goes like this. But now here I have the chemical potential to remove a particle is larger than the chemical potential to add a particle. That cannot be. And so in fact what we do is we stop where the two lines intersect. And this is the first Mott law. Everywhere here n is 1. We take n equals 2 and 3 and so on, and that will simply give us more lobes, more triangles like this. Okay, and here we have 2 particles, and here we have 3 particles, and the fact that the tip here is farther to the left than the tip here, and the tip here is even farther to the left, that's intentional. I'll show you this, that this, in fact, is what should happen. Okay? I'll show you that in a second, but then I will remind you first that all of this is at t equals 0. I have shown that this phase is incompressible. This phase is incompressible, and the incompressibility stops here. So everywhere here is compressible. So we went from a phase which was incompressible and which I had argued was an insulator to a phase which is compressible. just by crossing this line, either this way, or by going through the tip, we go from one phase to another phase at t equals 0. This is a quantum phase transition.